sort of straight. Okay. So factoring fundamentally is just, thank you, I want to make sure, yeah, is just undoing multiplication. So we know that from like factoring numbers. In fact, I'm going to take some abstract stuff you guys do, and I'm going to try to make it concrete and really show you what the heck you're actually doing, right? It gets very abstract. Do you guys agree with me? Yeah. Okay. So the most fundamental idea is the reverse of this idea. So I'm going to put like a little recall. So this is old stuff. How would you do, this is going to seem silly, how would you do this? I mean, how would you simplify this? This isn't factoring. This is just a simplification problem, right? What method would you use? Anybody? Like, all right, let me do a simpler example. What about, what would you do? How would you simplify that? What's that say? Can somebody just tell me what it says? 4, what's the operation? Times. Okay, beautiful. So how would I do that? How would I simplify? How would I carry out that operation? What would I do?
First, do the parentheses.
Okay, sure. Can you do x minus 7? What's x minus 7? I don't know, right? You're like, I don't know, purple, right? I don't know what x minus 7 is. We don't know what x is, right? So, beautiful point. Whenever you can do what's inside the parentheses, good old PEMDAS. You guys remember PEMDAS? Please excuse my dumbass son. Or dear Aunt Sally, right? Okay, I love it. I always have somebody in the crowd that's got a son. You're like, yeah, I don't know. So real quick, do you guys remember distribution? There we go. So what would that be?
4x.
28. I love it. Right? Cool. And then, of course, here, same idea, right? So what's 4x squared times x cubed y? What's the number here? 1. So 4 times 1?
4.
X squared times x cubed, how many x's you have now? 5th, right? 5 of them. Times y, right? You didn't pick up any more y's here. Minus, well, yeah, there, Jeff. 2 times 4?
8.
8. And then x squared, there's no more x's, so I just got those 2 x's and I got no more y's. Okay, so that's distribution. So I just want to do a quick review of distribution, because the first form of factoring, the most basic form of factoring that shows up in other forms, is GCF, greatest common factor. So all it really is undistribution. It's just undoing any distribution that was done. So for example, if I saw this, what do you got, John? Your thought process is, what would have been sitting in front of parentheses that would end up here? Right? So the way you look at it is, what can come out of both terms? You guys all agree with me there's 2 terms? Mm-hmm. What number could come out of both? What number could I kind of divide out of both? Because when I distribute, I multiply it in. So undistribution is dividing it back out. You're really just saying, what would the problem have been to end up here? A 3 can come out, but more can come out. 6. Right? How are you guys all feeling? You guys okay?
Still a little lost.
Okay. So let's back up a second. All right. Let's do a little more recalling before we do this. So if I have, for example, 2x times 3x minus 4. What do you get there?
Not x squared.
Careful. Times.
Oh, times, yes.
So 6x squared, right? Is that cool? Tell me if you're not cool with that part. We can talk about that part.
I'm just confused on how to do the steps.
I got you.
Yeah.
This, so distribution, the distributive property, is itself a single step, right? So I need to kind of feel out where everybody is. Factoring is undoing multiplication. So if you're not comfortable with the multiplication in the first place, we need to start there.
Mhm.
Because how can you undo something you're not even comfortable with doing in the first place, right? The more comfortable you are with multiplying stuff out, in fact, that's how I teach a lot of factoring methods, is I go back and say, remember when you multiply this stuff out, we're going to undo that. So we're going to get clues by looking at what we do when we multiply it out. Okay. So let me think one more step back. We'll come back to this. Real quick, I really want you guys to believe in distribution. If I have this, right, and I like what you said earlier, good old PEMDAS, you would try to do inside the parentheses first, of course, that's what P is, parentheses. But I don't know what the hell x minus 7. Take 7 away from some number I didn't tell you what it was. What do you get? And you're like, I don't know. The hell, I didn't know what you started with. So I can't do in here, right? So then you might think, now I really want you guys to stay with me. Then you might think, well, there isn't anything I can do. I can't even do the first step. But we know what multiplication means. Can somebody remind me, what is x plus x plus x, for example?
3x.
3x. So if I see 3m, how can I rewrite that?
N plus M.
M plus n plus m. What do I see here? 3 whats?
3x's.
3 x minus 7s. So if I wrote x minus 7 plus x minus 7 plus x minus 7, get your like terms together, what do you get? 3x minus 21. So what's the shortcut? We developed a shortcut. Distributive property really is just a shortcut. It says, why even do this stuff? I know I'm going to get 3 of these, and I'm going to get 3 of these. So that's where we came up with, and of course, thank God, math people, we do sometimes have a problem naming things. I don't know if you've noticed that, but distributive property is one of the best things. Distribute. Oh, beautiful. It's exactly what it looks like I'm doing. I'm taking this, and I'm giving it to everybody inside. Okay, how are we feeling so far? I love it. Okay, this is good. This is good. I really need to get down to this before we can move forward, right? Okay, so think backwards now. If I saw 5w minus 25, what would have been in front of what?
5.
Yeah, they both have a factor of 5, correct? And again, that's the whole idea of factorization. You're trying to take factors out, pull the factors apart. So if I put a 5 here, 5 times what is 5w? W. 5 times what is negative 25?
Negative.
Okay, cool. And then how do you check yourself? Distribute it back in. Okay, kick-ass, kick-ass. And again, dear God, I don't care if every other person in the room understands something. If you're like, I don't understand it, just speak up. Right? I like to say, if I'm going too fast, slow me down. If I'm going too slow, deal with it. Right? It's one of my favorite sayings, so I live by that. Okay. Okay. So let's ramp this up. This basic idea is built off of this fact, and then I can just take it. So let's come back to this guy. The way you do a lot of these GCF problems, I try to get my students to realize you don't have to think about the whole problem at one time. Think about numbers and then letters as they come. The numbers, what do they both share? We said this earlier.
6.
The biggest number, that's why it's G, greatest, the biggest thing, common, that they have in common, factor, that is a multiple of it. Right? So I can take a 6 out. Now look at the letters. There's only one letter, it's X's. Let's see if you guys get this. How many X's do they both have? They both have 1 X, right? This guy's got 2, but if I try to take 2 out, isn't he gonna freak the hell out? He's only got 1, poor little dude. So kind of call that the fair tax man in a way. They don't try to take more than you got, right? So again, what am I thinking? I'm thinking there was something that was multiplied by stuff to get this. So there was a 6 and there was an X. 6 divided by 6 is 1. X squared divided by X, X. right? Is that cool? I had 2 x's, I took 1 out, so I have 1 left. You can even say that to yourself. That's exactly the way that's exactly how this works. What do exponents mean? I have that many of those letters. So if I had 2 and I took 1, I got 1. That kicks so much ass. And then negative 12 divided by 6. I had an x and I took it. Aw. And how do you check it? Multiply back out, right? And real quick, this is almost too early to do this, but I want to show you this. Where's that? Oh, okay, close that door in a minute. This is a side note, right? Sorry. This is nothing you have to ever do. This is kind of cool though. I've noticed more books doing this. This is done. If the problem said factor this, you're done. Everybody with me? You're done. I'm about to do extra stuff. Because I'm a math guy. You do extra stuff and you're like, stop it. Okay. What could x be in that expression? What could x be? Give me an idea. What could it be?
4.
Anything. Could be 4. I love it. So what if x is 4? Just go. And again, you don't ever have to do what I'm about to do. I just kind of want to show you there's a concrete thing behind the abstract thing we just did. If x is 4, why 4? Because you said 4. Could you have said 7? Yeah, then I would have done 7, right? I can make it whatever the hell. If x is 4, this would be 6 times 16. Is that cool? Which is 96 minus 48, which I believe is 48. Neat. Is that cool? 6 times 4 squared, 6 times 16 is 96, minus 12 times 4, 48. 96 minus 48, 40. What is this if x is 4? 6 times 4, 24. 4 minus 2, 2. Is that factored in a way, right? Okay. Because, and again, sometimes people are like, I don't know what you just did, just a bunch of numbers. I'm hoping you understand what this is. When you factor this, you are factoring an infinite number of numbers at once. Because how many things could x be? Holy shit. So you would expect it to be a little difficult, and actually it's not as hard as factor an infinite number of numbers for me. We just did. Bam. It's all extra, by the way. You guys with me? Everything in green is extra. Okay, I really want you with me, but I really like showing students this because you make x any number. It's a way to check your work even.
I was about to ask, is that a good way
Yeah.
to check our work?
Yeah, if you have time.
If we just set x to a value and then solve both.
Total. It's really nice if you're allowed to use your calculator, right? But yeah, if you have time, make the letter something, and then see what this is, and see what your answer is. They have to be the same because that's what this means. This would become this. So this better become this. Maybe. No, yes, maybe? I really, so much.
Yep.
Okay. All right, real quick, you're gonna help me out. Okay. 5 times 7 is,
Oh, me?
yes,
Oh. 35?
35. Okay, now watch, stay with me, Again, see this is in green? Green for right now means extra, right? So what if I said x is 5? How would I write 5 times 7? Well, x is 5, right? So this is x. If x is 5, how do I get 7? What do I do to 5 to make it become 7? How much do I add to 5 to make it become 7? 5 plus what is 7?
5 plus what is 7?
Yep. What do you add to 5 to make it 7?
2?
2. So then, wouldn't that be 5 plus 2 is 7, right?
Mm-hmm.
Okay, and isn't 5 what we call x?
Yes.
Okay. Okay, now stay with me.
X.
So, I'm kind of doing what we did over there, just kind of backwards, right? 5 times 7 is 35. If x is 5, 7 must be x plus 2. No question, right? If x is 5, x plus 2 is 7, right? If I multiply this out, I get this, right? Is that cool? X times x is x squared, x times 2 is 2x.
Mhm.
If x is 5, isn't this 25? And if x is 5, isn't this 2 times 5, 10?
10. Yep.
And isn't that also
35.
35? Okay, so when I multiply two things together, I get a result. When I'm trying to factor something, I'm trying to pull it back apart. When it's written in terms of x's, things are more abstract because we don't know what the number is.
Mm-hmm.
But watch this. Let me go one step further. You ready? Okay. So see how we said x is 5, and that meant this is 5 times 7? What if x was 8? What would this be? This would be 8 times, if x is 8, 8 times
8?
8 plus 2, right? If x is 8,
Yes.
this would be 8 times 8 plus 2. So 8 times 10.
10? Okay.
And this would be, if x is 8, this would be 64, 8 squared, 8 times 8. Right, so let me write this out. If x is 8, this would be 64 plus 16, which is also 80. Okay, so that's just side notes about what I mean about letting x be anything.
Okay.
So one thing as an algebra student that you're not really comfortable with, because you don't get to play with it much, is the fact that you know x could be anything you want it to be. So whenever you do anything with variables, it's the same thing that has to happen with numbers. They have to, because what are variables? They're just numbers I don't know yet. So all the ways that numbers act, variables have to act the same way. So, let's see. So coming back to this, and again, this was all a side note, kind of all related to a way to check GCF. In fact, check any form factor. So let's come back straight up to just how to analyze this kind of problem here. Let me make it a little more interesting. What do you got, Jeff? Not too crazy. Okay, I like it. So we know that this GCF problem came from something sitting in front of parentheses. So this is what we call undistribution. The most fundamental place something could have come from is something sitting in front of parentheses. So I would have distributed. So I'm trying to think backwards. I'm just trying to think backwards. So look at just the numbers. What do they both have in common? 7. So it would have been 7 times something. So we're going to leave some room. In fact, let's go ahead and do this. This is not, I wouldn't recommend it. Let's do this for this problem. 7 times what is 14? 2. And 7 times what is 21?
-3.
I like it, right? So far, all we did was realize there is a number that when I multiply by these two different numbers, I get what's there. So I'm just trying to figure out backwards. What must have been sitting in front so I would have ended up with this? And then what has to be inside to make that happen? Now look at the letters. So look at the numbers and you think, what's the biggest number that goes into all of the numbers? And that's what you put out front. Now look at the letters. How many X's could you possibly take out? He's got 2, he's got 1. So the most X's you could take out is 1. Couldn't they both give you an X? If you had $2 bills and you had $1 bill, how much could I take from, like, if I take the same amount from each of you, what could I take away? 1. If I try to take $2, you're fine. You got $2.
Yep.
You got $1. You're looking at me like, I can't give you $2. You're crazy. So that's why here we're always trying to figure out what is the biggest thing that everything could give, right? So he could give 2, but this guy's like, oh shit. So I take out just 1x. So what's the shortcut with variables then? The smallest power is the number I take out. Does that make sense? So what's the smallest power in the y?
It's 3.
3, so that's how many you take out. So I didn't like doing this 2 and 3, but I just want to show you where it kind of goes together. Once you've got this written down, then you just take each term one at a time. 14 divided by 7 is 2. I had 2 x's, I took 1, so now I have 1. I had 3 y's, I took 3. So now I don't have any. Is that cool? You can say it exactly like that. And just to check real quick, 7 times 2 is 14. X times x is, and y cubed times nothing. Like, there's really 1 there, right? Okay, maybe. Now do the same thing here. 7 goes into 21, 3, put the minus sign. I had an x, I took 1 out.
So it's X.
No x's. I had 4 y's, I took 3. There's 1 y. Okay. So I like to explain concepts on the side and behind things, but that is all you have to worry about with a GCF problem. You do numbers, then you do the letters as they come. You look for the smallest power, right? And then you write what's left in each term. So let's try one that's a little bigger. So what if I had something like, oh shit, here we go, Jeff. All right, let's see, 30 a squared bc. Yeah, minus, oh, Jeff, what, 10 a b squared c cubed plus, what else you got, buddy? Yeah, 15 a cubed b c to the 4th. Okay, I love it. You would, Jeff. Sorry, give myself some shit as I go along. Okay. All right, math boy. So there's 3 terms. We don't care. We just do the same thing one more time. Okay, so you gotta be a little more careful with 3 terms, but now I've identified green as not necessary, unfortunately. Okay, so I do want to use some different colors now. Look at the numbers first. What number can come out of all 3? All 3 numbers. What can come out of all 3?
5.
Yes, good. Can't be 10, right? Because 15 doesn't like 10. I can take a 5 out of all 3. What about, is everybody cool with that?
Yeah.
Now look at the letters one at a time, and now that we know the shortcut, and we understand why the shortcut works, I don't know, this poor little dude. I can trust you? Yeah. Where am I? Okay, I'm there.
1
Yeah, so there's 2 A's, 3 A's, but this guy's only got 1. So you look for the lowest power, because if you try to take more from that guy, he'll freak out. Right? So you take 1A. What about the B's? 1B, right? He's got 2, but the other guy's only got 1. And then, of course, the C's. Yeah, this guy's got 4 C's, he's got 3 C's, but he's only got 1 C. So you can only take out 1 C. Okay. And again, real quick, going back to this real quick, I really want this to make sense. How many terms are inside? 2 terms. What are they each getting if I multiply that problem out? What are they each going to get? Aren't they each going to get this? That's why I'm thinking, what can each one of them give back, right? Sort of like I gave them something and I'm going to take it back. So, and notice this is a little point, but this really helps out. You see how I put this back here? So now when I write what's left, I can do it underneath each term so I don't make a little mistake. We are our own worst enemies in terms of writing math down. We kind of write it in a way that kind of gets in our way. We lose things, right? So here, 30 divided by 5.
6.
I had 2 A's, I took 1.
1A.
1A left. I had 1 B and 1 C, and I took 1 B and 1 C, so
Nothing.
nothing. And I can check. 5 times 6 is 30. A times A is A squared. B times C is there, BC. So far looks good. Minus 10 divided by 5. 10 divided by 5.
2.
2. 1A took an A.
No way.
Nope.
2 B's took a B.
One.
1 B. 3 C's took a C.
2C.
C squared. I love it. Plus. Good. 3.
A squared.
A squared.
No B.
No B's.
C cubed.
C cubed. And again, believe it or not, we're not going to do it, but if you let A be something, B be something, C be, and you plug it all in, that would be a number, and this times this would be that. That's the way it is check again. But this one's kind of gross to trying to check. Yeah, you have to give 3 values for these 3 different letters. Okay. Okay, maybe. How you guys feeling? Are you feeling better?
Mhm.
You don't have to feel perfect. You feel better about that. Okay. That's all GCF needs. And again, distribution is multiplication, so undistribution should be division. So let me do one little extra GCF thing, and then we gotta keep moving. Oh, we gotta really keep moving. The one little GCF thing that really confuses people. So let me just make it exactly just that. You do it, Jeff. Yeah, let's just make it nice, straight to the point. Okay. Very unassuming little problem. It is easy. There's one thing that you have to be careful about. Go ahead and try to do this. And it's nothing tricky. There's one thing you have to be careful about. I kind of helped there. Let me not do that. Sort of do the mistake. I'll show you. So you think about it the exact same way. You don't have to know ahead of time something weird's going to happen. GCF is just always GCF. So what are you guys taking out? Let me make sure we're all on the same track. What are you guys putting here?
2.
Yeah, so look at the numbers. A 2 can come out of both. Look at the letters. The smallest power is a first power. Is that cool?
Mm-hmm.
So you always can, I don't care how many letters they got jammed in that thing, you just do them alphabetically, right? Just see who's the lowest power, take that many. Who's in the next one? So what's left here? 4 divided by 2? 2. Had 2 x's, took 1.
1x.
Now here's the mistake I see. I had 2x, I took 2x, so I'm done. Why is that a mistake? How can you tell immediately that if somebody said that's the answer, they're wrong? You get the same thing if you multiply it back out. 2x times 2x is?
4x.
What happened to him? So, tell me again, what is it when I undistribute something? What operation is that? Because when I distribute, it's multiplication. It's division when I take it out. So what is 2x divided by 2x?
1.
1. There you go. It's like a placeholder, right? If I start with 2 terms, this better still have 2 terms, or else I can't create a term if I want to try to check. I want to multiply back out. Okay. I like it. So you see that? So the funny thing about GCF is it never changes. Do the numbers, do the letters, and once you got this written down, you just take each term one at a time. Beautiful. So, the next level above this is something called grouping. So I want to first start with the most confusing part of grouping, which is a later step. So I'm going to start at a later step. What do you look like? Okay. So what if I had this? Might not be the best for a little pink dude. Now, real quick, I'm going to do a problem on the side that's related to this somehow. So what if I had this? This is no trick, nothing. It is really simple, straightforward. If I said factor this, what is the only thing you can take out? What's the only thing they both have?
Y.
A y. You guys see that? Can something come out of 5 and 6? No. X, there's no x's here. You can't take, the only thing you take out is the y, right? And of course, what's left if I take a y out of each? 5x plus 6. Now, do you guys see, does anyone see, that is the exact same as that? These are exactly the same problem. What is acting like y over there? X minus 7. Isn't x minus 7 a number? It's one number, isn't it? If x is 10, it's 3, right? But it looks to us like it's more than that. But it is really just one thing I don't know. So what do both of these have in common? Well, the numbers? No. This has one x, this has, no, be careful. Let's see if you guys think I'm insane. There's no x's here. I don't see any x's here. Does anyone have a problem with me saying that? Some of you should. Real quick, is there a 5 in 10? Yes, why? Because 10 is 5 times 2. Is there a 7 in 10? No. 7 times no whole number makes 10. But isn't 10 7 plus 3?
Mm-hmm.
So when we say in, we inherently mean a factor of. Right? It's something that multiplies to become that thing. So this has one x, this has no x's. This has an x minus 7. This has an x minus 7. So what can come out?
0?
No. What do they both have? Don't overthink it. What do they both have? What did we just say?
X minus 7.
X minus 7. They both have x minus 7. See, it's just like this. What is y? Can somebody tell me what y is? I don't know. Shit. Could it have been x minus 7? Yeah, because I don't know what y is. Maybe it is x minus 7. I don't know. Whatever is common to both can come out. I don't care what it looks like. Right? So then what's left? And here's what's funny. Just cover what you took out. 5x plus 6. Kick ass. And check it. What is x minus 7 times 5x? Oh, there it is. X minus 7 times 6. Bam. Right? Oh, shit. It thinks we're all gone. I think it's way. So, let me ask you this real quick. What's your name again?
Crystal.
Crystal. Is it C-R-Y?
Yes.
No way. Okay. I guess. Perfect. So that's the answer to that. So 5x times Crystal, like that,
Mm-hmm.
plus 6 times Crystal. Okay. What's common?
Crystal.
Yeah. So I can take a Crystal out. All right. So you can tell everybody I was in a math problem. Multiplied by 5x plus 6. It felt kind of weird.
No.
I don't care what that thing is. I don't care what it is. If it's the same in both, it can come out. And that makes sense because distribution gives each thing the same thing. That's why I'm looking for what's the same. That must be what they both got. Okay, maybe. So, I told you this problem shows where people have trouble with grouping, but it's not really grouping. So let's do grouping, okay, which leads to this kind of thing. And by the way, on my handout, I've got, I call the zeroth step GCF. You always try GCF. I don't care what's going on. You always try, does something come out of everybody? Because it's going to make your numbers smaller and all this kind of stuff. Second thing you try is grouping. If there's 4 or more terms. So, if I see, should really be numbering these, but do it. If I see this, let me see if I can make one up on the fly here. Should be a neat. You can do it, Jeff? Yes. Can you do it, Jeff? Yes. I can do it, yes. Okay. Let's see if that works. Yeah, cool. Okay. Are there 4 terms? Yes. Is there anything that comes out of all 4 terms? Do you see how he's got no B's and he's got no M's? That's a 5 and that's a 12. No, right? I don't even care. I don't have to look at everybody because those 2 already don't share anything. There's nothing that all 4 share. Yes? So it seems like, oh well, Jeff, we can't do anything. Too bad. So anybody know what grouping means? In this case, yes.
You just do the first 2 together and the second 2.
Yes. So I always tell students, don't put parentheses, put little underlines. There's the first 2, there's the last 2. They become 2 little grouping problems. 2 little GCF problems. What comes out of the first group? M. Don't worry about him yet. Right? Is that cool? And then what's left, of course?
5M.
Yeah, 5M minus 6, because I took his M. Poor little guy. Plus. Now here's what's really cool. What was the only reason we were able to do anything with this one? Because this was exactly the same as this. If there's nothing the same, I can't GCF. I can't do it. So what better be in here?
5M.
This, yes. So it actually gives you a clue. So what do you want to take out? And okay, you don't really need this clue because the numbers aren't too crazy. But what comes out of 10 and 12?
2B.
2. Yeah, and then you can take a B out, 11. But if you had gross numbers, you could actually use that. I want a 5 to show up, so of course I want to take a 2 out. I want an M, so of course I got to take a B out. So 10 divided by 2 is 5. And then MB, and I lose a B, so I just have a M. Negative 12 divided by 2 is?
-6.
And I had a B and I took it. So what tells me I'm on the right track?
5M minus 6.
These are the same. If there was nothing the same, I did something wrong, or what do you call a number you can't factor? Prime. It could be prime. They could give you, no, they're not going to do that a lot, but they could give you problems where it's just not factored. This one is, because of the same. So we do the same thing we did here. So what is this term? Here's where people really freak out. There's only 2 terms up there. There's only 2 terms. What do they both have in common? 5 and minus 6. Does either term have a 5 in it? No, neither term has a 5 in it. I really, that's going to take a while, right? And I love it when I tell my students that I can see someone look at me like, do you know numbers? That's a 5, my man. But you understand what I mean now. It's a factor. Neither one has a 5. But they both have a 5m minus 6. Because it's multiplied by stuff. So what's left, that's beautiful. Now you just got to cover. M plus 2b.
2B.
Or not to be. That is. Whether it is noble, it is not. You want a math guy suddenly doing Hamlet. It's all weird. And then, of course, how do you check this? Well, what method would you use to multiply this out? Kind of a little mnemonic device. I actually don't want. What do you wrap potatoes in if you want to bake? Foil. Foil it up, right? I hate foil because it makes it sound like, oh, I've got to remember this FOIL. Because you don't. You just distribute the 5m and then you distribute the negative 6. It's just 2 distributions, right? That's all foil is. That's how you would check it. Kick ass. Or, of course, you could do, if m is 6 and b is 3, blah, 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 that thing, but could take a little while. Okay. Now, let me see. Let me give you, what time we got? Oh, yeah, so little time. I'm sorry, guys. Yeah, let me do this. Let me keep going, and then I've got a bunch of handouts to give you, and I'm considering making an answer key for the one, especially now that we don't have really enough time to kind of go through it all. The next level after GCF is when you do like, this is almost like the classic factor problem, the 3 terms, right? So let me write a problem up here and just see what your take is. Right? Your classic trinomial thing. So I have a handout that's called, I call it the motivation handout. I want to give you guys motivation as to why the method we use makes sense. So let me kind of go over it with you, and then of course you can reference the handout when you're all by yourself. Can you guys real quick, just for me, just multiply this out? Just FOIL that bad boy out, right? I did not bring, yeah, you guys FOIL it out. I'm going to grab some more. So what do you guys get?
X squared plus 5x plus 4x plus 20.
Yeah. And of course, what can you do with those two terms in the middle? Yeah, so you get x squared plus.
9x.
All right, let's do one more. In fact, let's do one with some minuses in it. X minus 3, x plus 2. Now I want you to notice something. Everybody get that there? Okay. Notice this. How does 9 relate to the numbers that were there to begin with? Add them. 4 and 5 make 9. How does 20 relate to the numbers that were there to begin with? 4 times 5 is 20. Right. Let's see if that holds. What's negative 3 plus 2? Negative 1. What's negative 3 times 2? Negative 6. Okay. And of course, whatever numbers I throw up there, the same thing's going to happen, right? Exact thing. Of course it is, because the middle numbers go in the middle. Those are like terms. Of course they combine to be the middle coefficient. So in mathematics, we look for patterns to develop processes to do things. Very often to do things backwards, right? Because that's what algebra is really good at. 6 and 7, 4, 2, great. Now do that backwards, and then bring variables in. Okay. So this guy, what I want to do, does this make sense to put x in x? Because that's how I get, of course, x squared. So the whole problem boils down to a puzzle. What two numbers multiply to be the last number and add to be the middle number? So what two numbers multiply to be positive 6 and add to be positive 5? 2 and 3. Done. So when the first number is a 1, this is a very straightforward number puzzle. Right? In fact, I like to start with that with people. So for example, let me do this. Let me give you the sheet. Yeah.
Thank you.
And then, so look at the top there. Look at 1A. Can you tell me two numbers that multiply to be, don't tell me yet. Think about it. 24 and they add to be 11. Don't say it yet. All right, so what two numbers multiply to be 24, add to be 11?
3 and 1. Wait, sorry, what did you say?
Multiply to be 24, add to be 11, right?
4.
Yeah, 3 and 8, sorry, I said 11.
3 and 8. So what's one way you could do that? You could make a list of things that multiply to be 24, right? 2 and 12, 1 and 24, 4 and 6, and eventually you'll make it to 8 and 3. Or you could make a list of things that had to be 11. And then check, right? So you just need two numbers that add to be the middle number and multiply to be the last number. That's it. But why? Why do we need that? Because that's what happens, right? That's what we see happens. Does this sound familiar to anybody? All right, all right. So, try 1B real quick. There's some negatives at you. You guys all see that? It's the side where it's the form. It's where it says number 1, right? The other side says number 2. So 1B is a little more of a puzzle. They got to multiply to negative 40 and add to 6. So again, if you're allowed to use calculators, okay. If you're not that quick with what multiplies to be something, okay. So the most standard way is to get a list of these and then check this. I personally like starting here, right? But now tell me this, if it's going to multiply to be a negative number, what's got to be true about the two numbers? Can they be the same sign? No, they have to be different signs, which means they actually subtract to be 6 because they're different signs. So me, I would do this. Give me two numbers that subtract to be 6. So maybe like 8 and 2, right? Right. So if the 2 is negative, that makes 6 when you add them. But 8 times negative 2, is that negative 40? Nope. So you just go bigger. 10 and 4. And 10 times negative 4 is? So those are the numbers. Now real quick. What would this look like in an actual algebra problem? It would look like this. Whatever's last, it's got to be what they multiply to be. Whatever's in the middle, it's got to be what they add to be. I really want this to make sense because how do I make x squared? What goes here and here to make x squared? X and x. Now that's, I know that. I know it's x and x. The only thing I don't know is what the numbers that make it work. And I know the numbers will add in the middle terms and multiply at the end. So what two numbers? It would be positive 10 and negative 4. And just to make really clear, because sometimes I have students that don't understand. If you wrote this instead, are you still right? Of course you are, right? Is 6 times 8 different from 8 times 6? No. So as long as you got an x plus 10 and an x minus 4, multiplying, you're golden. If I said factor 18 and you said 2 times 9 and somebody said 9 times 2, is one of you wrong? Not really, it's the same thing. Okay, all right, I like it. So you guys go ahead, try out A and B down there at the bottom, right? A and B. Does anybody have to leave it? Well, that's clock says 2, but anybody have to leave at 1? I could go a little bit past if.
I have tennis at 2, so.
Okay. I'm
I'll
not
have
going to go
15
too far
minutes.
past, trust me.
No, it's fine.
Yeah. Okay. So this is something you see a lot in math is knowing what part of the problem to focus on. You don't ever have to have the entire problem in your head. A beautiful example of breaking the problem into parts. Does that make sense? So you need two numbers that do two things.
Mm-hmm.
Yes. So what can you always do for yourself when you see a trinomial with a 1 in front? You can always just put x and x. So your whole world for this problem is, what are the two numbers that go at the end, right?
Mm-hmm.
So you need two numbers that do what? What do? They have to multiply to be 12 and add to 8. So what two numbers multiply by 12 add to 8? 6 and 2. And it doesn't matter where you put them as long as they're both positive, right? Because that's positive, that's positive, everything positive. Okay, I like it. Go ahead and do bar B if you haven't yet. Just to help you out a little bit. Do you see how that last number is positive? And that's what they multiply to be. The only way two numbers could multiply to be positive is if what? They're the same sign. If they were different signs, they'd be negative. So you know they both have to be positive or they both have to be negative. The middle term tells you they both have to be
Different sign, negative.
negative. They both have to be negative. Because they have to add to be a negative. I know they have to be the same sign, so they multiply to be positive. They both have to be negative, so they add to be, I'm sorry, they both have to be the same sign, so they multiply to be positive. So they multiply to be positive. They both have to be negative so that you get the middle term. Okay. So again, I can write my x and my x, and I'm totally focused on the numbers. And again, you could either make a list of things that multiply to be 20, right? 4 and 5, 2 and 10, oh. Right? So what are you going to put inside? Minus 2, sure, or minus 10. Either one first, yeah. And how do you check? Well, negative 2x minus 10x is negative 12x. Negative 2 times negative 10 is 20. And you know x times x is x squared. That's why we put those. So we already had that covered. There's just the numbers we had to figure out.
Mm-hmm.
So we boil it down to just a number game. In fact, it's a number game. You could ask somebody, like in 5th grade or something. It doesn't have to be algebraic. It's just give me two numbers that had to be this and multiply that, and they have to kind of tease it out, right? So you just sort of boil it down to a number puzzle. Now, one thing I want you to realize that I keep saying in each problem, you see how they're all a 1 at the beginning? Okay, the minute that's not a 1, things get freaky. And I want to show you why, and then I want to show you how to do it. Then I want to talk about cubes and squares, and then I think I have to stop, right? Because I got stuff going on at 1:30. Let me see. Okay. So remember, if I multiply, real quick, if I multiply these out, you don't have to write this down, I'll get the middle terms combined directly, right? These numbers are right there. I really want this to make sense. That's why it's really simple. These numbers didn't change here, and 4 times 3 is 12. So everything is 4 and 3. 4 and 3 are doing things. Okay, and you're all like, I don't know what you're talking about, Jeff. All right, here's what I mean. The minute I have like another number here, not just 1. So there's a 2. Let's see what happens. 2x squared plus 6x plus 5x plus 15. So 15 is 5 times 3. 12 is 4 times 3. I see a 4 and a 3 in the middle. Do I see a 5 and a 3 in the middle? Do I? I see a 6 and, oh shit. And again, I don't know if you guys really get what I'm saying. At the most fundamental level, the way to factor this has to be a little different. Because this was so simple, because 4 and 3 do everything I need them to do. They make 12, they make 7. Here, do 5 and 3 do everything? Do 5 and 3 make 11? Right? Isn't that what I'm going to get in the middle? Do you see what I'm saying? Do 5 and 3 make 11? Shit, no. But they do make 15. And you're like, oh man, I can't quite do it. Because that silly 2 multiplied and messed things up. So when there's a 1 out front, nothing gets confused. The numbers stay the same. They're very direct. The minute there's another number that's not a 1 out front, that messed some stuff up. It doubled a part of my, oh man, so I can't look at it as neatly as we did these. These are beautiful, man. That's why you love a 1 out front. Notice this though. I'm going to do another one of these. What's 6 times 5? 30. What's 2 times 15? Okay, hold on to that. Now you guys help me out. I want you to know I'm not just making shit up that works. Somebody give me 2 numbers. 11, sure. Maybe something, give me another number. And go ahead. 8, all right. I love you guys, are. All right, nobody's saying square root of 3, which is good. Let's stick with relatively smaller integers, right? Somebody give me a number. 2x. Okay, somebody else give me a negative number.
-5.
Negative 5. Okay, I love it. All right, so I got nothing to do with this problem. Right? It's all on you guys. But let's see if the same thing that happens again, because maybe we can make a process off of it. So one thing that my students hate when I teach them is that I show them everything, and they're like, just tell me how to do stuff. But I really want you to see, this isn't just shit we just went, let's do it this way. It's just what we saw. It's what we saw. And then we made processes off of what we saw. So I want you guys to see the same thing. So if I FOIL this, I get 22x, is that cool? Squared. Minus 55x plus 16x minus 40. Now, somebody help me out. Before I combine the middle terms, what is 22 times 40? Well, that's not too bad. 22 times 4 is 88, and then I just add a 0 on. Is that cool? 22 times negative 40 is negative 880. Is everybody cool with that?
Mm-hmm.
What is negative 55 times 16? Watch this. This is kind of cool. I want to show you a little something. Negative 55 times 16, right? Right? Stay with me. Isn't 16 2 times 8? So isn't that the same problem? What's 55 times 2? 110. What's 110 times 8? 880 again. So what is the thing? I noticed that this times this was the same as this times this. I noticed that this times this is the same as this times this. Always. You guys made those freaking numbers up. So I didn't make that happen. It just happens. It's the way that they work with each other. And now your question is, great. The shit does that mean for me, right? You probably wouldn't ask me that way, but isn't that your question? Like, what does it do for me? So, let's see. What if I had? So notice, this times this is the same as this times this, right? So what if I had? Okay. So this number right here, it came from 2 places. It came from this first thing times this last thing, right? And then it came from the 2 middle ones. So on this problem, I can figure out what its number is. Can't I take the first times the last?
Yes.
4 times negative 6 is? Negative 24. Now, what are factors of it? Do you see how 55 and 16 are factors of this that add to be, they're going to add whatever they add to be? I think it's 39, all right. So if there was just not a 1 out front, I would just find factors of this that add to be this. The minute there's something that's not a 1, I have to take it into account because it's going to mess things up. So I don't take factors of negative 6 that make negative 5. I take factors of negative 24. Now, what factors of negative 24 add to be negative 5? Think about it like this. What factors of 24 are 5 apart? How do you factor 24? Give me some factors of 24. 2 and 12. 3 and 8. 8. 3 and 8, right? Which one's got to be negative so that this would be negative?
8.
The 8's got to be negative. I love it. Now, here's what you guys are going to just so love about this process. You cannot just do x plus 3x minus 8 because that doesn't make any sense. What's x times x? Is it 4x squared? What's 3 times negative 8? Is it 6? Yeah, no. So we actually have to do this process perfectly backwards. So what does that mean? Take negative 5x and break it up. using these numbers. Isn't negative 8x plus 3x, isn't that equal to negative 5x? So I'm doing exactly what we just did, just in reverse. How many terms are here now? What method can I use then? Grouping. So when you see a number out front that's not a 1, you have to take into account. And then the numbers you get are how to break the middle term up. Right here on this step, how many terms are there? The minute I FOIL it out, how many terms are there? 4. So all we're doing is we're taking this and going back one step. Because now, what comes out of these two? Comes out of these two. What's the number that comes out? 4. You guys are like, please stop. Okay. I'm trying to finish. I'm sorry. We should have coffee in here, but we don't. Or your favorite caffeine, whatever it is. How many x's come out? 1. So then 4 is gone. I lost an x. Negative 8 divided by 4 is negative 2. I lost that x. Is that cool? Plus, what comes out of these two? 3. Lost the 3, so I have an x. 6 divided by 3 is 2. Am I on the right track?
Yes.
How do I know? How do you know?
X minus 2.
These are the same. So that means since these are the same, I can take them out, right? I can take an x minus 2 out, and then what's left? 4x plus 3. So that's this guy factored. And again, remember, this is an infinite number of numbers. That's what this represents, because x could be anything you want it to be. And that's why this is relatively hard. But if I said factor an infinite number of numbers, you would think it'd be more steps than this, to be honest, right? That's relatively few steps. All right, so last couple things, kind of a little too quickly, and then I've got a couple handouts, and then I'll let us all out. I'm sorry I didn't quite get through everything I wanted to, but just want to make sure you guys are all on the same page. Let's see, yeah. All right, look at that guy. So that's very different. He's only got how many terms? 2 terms. So 4 terms grouping, 3 terms are trinomials. You do the stuff we just did. 2 terms doesn't seem like they should work. But can somebody tell me, if there's a missing middle term, what must it be?
1.
No, because then it would just have a plus 1 in the middle. If something's missing, what must it be? 0. So, I need 2 numbers that multiply to negative 9, add to be 0.
Oh, 3 and negative 3.
3 and negative 3. So the shortcut is, if I see 2 terms and they're both squares, yes, 9's a square, x squared is like in your face a square, right? I have 2 x's, 1 here and 1 here. I have 2 3's, 1 here, 1 here. Plus minus so that it multiplies be negative, right? So I call difference of squares problem, thank God, or thank your favorite deity, thank the flying spaghetti monster, thank whatever thing, right?
Mm-hmm.
I don't care if there are 2 terms and everything is squared, you go, oh, thank God, or thank whatever, right? So for example, if I saw, let me see if I can step this up really quickly. A squared b to the 4th minus 49 x 4y 8. Oh my God. Can you cut everything in there in half multiplicatively? Can you cut everything in half? You guys agree? Totally. And I mean multiplicatively, right? So 49, you could break it up as 7, right? So watch, this is 2, and it's a minus. So 16 is 4, 4. A squared is A. B4 is B squared. Plus minus or minus plus so that the middle terms cancel, right? 49 is 7 times 7. X4 is X squared. And Y8 is Y4. I mean, that, holy crap, that's so nice. Because everything could be cut in half, you do it, right? So if this is half of this and this is half of this, they multiply to be a whole of this, yes? Oh, they come together. Oh. this is half, they multiply, become a whole of this. And then the middle term, do you guys see how it cancels? Plus 28 stuff, minus 28 stuff. Middle terms cancel because it's plus minus. So people don't have faith in the squares. Like, that's too easy. Well, yeah, it's too nice. Awesome. If you can identify it as squares, easy. So how would you factor this? M squared minus 81. Yes, M. And M. And what's 81? Break it down. Tear it apart. What's 81? What times itself?
9 times
9 times 9. And the last step is just to put
9.
plus minus. Now, real quick, what's wrong with this? Why won't this work? Oh, shit, Jeff. You got it. That will not work. Because if you think it's x plus 7, how do you know you're wrong? Do the middle terms cancel? So this is x squared plus 49 plus 14x. Oh, is that part of what it's supposed to be? So that can't equal this because they don't become the same thing. What do you make them both minus? Same problem. Now you have negative 14x. Why can't they be minus plus? Because they're supposed to multiply to be positive. So sum of squares, you cannot factor. For pretty much the same reason you can factor difference of squares. Okay. And the last thing we'll talk about, because I know I'm sort of, like, please stop. Okay. We got to talk about cubes very quickly. Cubes are people's most hated ones because you just have to memorize how things fall into place. But I want it to make a ton of sense. Look at x squared minus 4. That's 2 of everything. So I put 1 there, so I put the other one there. I put 1, 2 there, so I put the other 2 there, right? Beautiful. Now watch this. What if I had x cubed minus 8? There's not 2 of everything, right? X cubed is obviously 3 x's. What's 8? 3 what's? Multiplying. 2 times 2 times 2. Yes? So I show my students, you put x times x times x. 2 times 2 times 2. Little dude, big dude. You'll see why in a minute. Right? So if I put 1x here, the other 2 have to go there. Same idea. 1 here, the other 1 had to go there. You guys with me? There's only 2 things. Now I've got 3 things. Damn it. So what if I put 1, 2 here, well, the other 2 2's have to go here. So you see how I'm getting my x cubed? If I make this a minus, do you see how I'm getting minus 8? Do you guys see that? Mm-hmm. So then some of you guys might say, why you left space, Jeff? You're done, right? Why am I not done? Because I also get negative 2x squared. Do I want negative 2x squared? Is that a part of the Is that a part of it? Shit. And then I also get 4x. Do I want 4x? No. So I need a term here that will clean these up, that will cancel those. And what always works, is whatever this is times whatever this is. Opposite sign. Why does it make sense? It's got to be the opposite sign so it can cancel stuff. Opposite sign, this times this. Now let's see what that just did. What did that just do? Well, so this is my new term I just put in there, right? What's x times 2x?
2x squared.
Positive 2x squared. Kills that. What's negative 2 times 2x?
Negative 4x.
Negative 4x. Kills that. Which means all I get is x cubed minus 8 because this guy killed all the middle stuff. So what is this? How does this look? When I see I have 3 things, 1 of each, 2 of each, product in the middle. And That's why people don't like cubes, because it's more of a memorization thing than the other. The other ones you can sink your teeth into and actually do stuff. This one's more like, gotta memorize this stuff, right? And here's a little mnemonic device. This is always going to be the same sign. This is always going to be the opposite sign, and this is always going to be positive. Soap, right? Good old soap. Because I don't know, have any of you ever seen Pulp Fiction by chance? Yes, no? Yes? You remember the scene? It's a terrible scene, but you have the cleaner has to come out because this unfortunate thing happens in the backseat. So I always think of this guy as the cleaner. He takes care of the stuff you don't want. Yeah, so. Oh my God, that was so fast, I'm sorry. But here, let me give you this one. This one is really important. It could be a little overwhelming, but
Thank you.
I try to put at the top a quick reference guide, and then I have like major explanations and examples for each thing. Does that make sense? There's a GCF, 4 more terms, 3 terms, 2 terms, and then front and back there's explanations of each thing, right? And then I gave you the motivation sheet, right? This is the one that I think I'm gonna try to get maybe even like a solution video, and then I can email your instructor so you can go to the video and see what I can do. But that's just some practice stuff. If you want to, I'm almost certain you've got some practice stuff from your teachers maybe already, so you don't have to do that obviously, it's just if you want to, okay? But I can email Corey and Nimi and just give them the link if they can share that. Yeah, so if you want to see solutions, I'll try to put a video together for you. By the way, have any of you ever been in the Math Study Center? So that's the Math Study Center right there. Tutoring is happening right now, right? And I'm sort of in charge of the Math Study Center. So yeah, your instructor should definitely have information about tutoring. It's free in there. We're open 8 to 6 Monday through Thursday, 8 to 1 Friday. There's online tutoring. It's crazy. There's tutoring by appointment online too. Anyway, so there's all kinds of resources. So feel free to come back out. So hopefully this is useful. Sorry it was jam-packed. They really didn't give much time. But yeah, so please do come back anytime in the semester if you need help, okay? Oh yeah. Do you guys need me to sign that?
Okay.
Sure. Oh, let me see. Can I borrow your pen real quick? Thank you. Yeah. Oh, you're good. Yeah. All right, guys. Please come back.